Hello and welcome to this lecture on chemical process modeling and simulation. We've got a nice introduction to the kind of chemical engineering problems that chemical engineers, process engineers face in their careers. Got an introduction to modeling in general, mathematical modeling in particular, modeling of chemical systems, units and processes even more specifically, and sort of understood in an introductory fashion a broad framework of how modeling happens, modeling is done, a recipe for modeling, what are the various steps involved, and then we started our journey into chemical system models, chemical process models. The first thing we did in that first step in that journey was to sort of learn the different types of variables, stream variables, unit variables, and process variables, and how to identify them, what they are. Now we have to look at the next step in this lecture, which is basically the different types of relationships that exist between these variables. Now, we also in the introduction try to understand the different types of relationships that exist between chemical process system stream variables, right? They are either equality relationships, which means they are equations, or they are inequality relationships, which are sort of bounds, maximum, minimum, ranges, limits, and whatnot, right? And there are also some sort of definitions which arise as relationships between these variables, which are of course equality uh, constraints as well. Now, when we are looking at equations, we also talked about there are basically two types. Basically, one is conservation equations, and the other are constitutive relationships, right? The constitutive relationships provide expressions for various terms that are present in the conservation equations. This was something that we talked about. Now, we are in this lecture going to get a broad introduction to the conservation of transported quantities in chemical systems. And this is of fundamental paramount importance. You can imagine in your chemical engineering curriculum so far, you have learned about transport of fluids, partly transport of solids, including some bit of an introduction to transport of granular solids, and then you've learned about transport of energy, heat in particular, as well as mechanical energy in different forms of energy. Transport of energy by way of transport of species or by way of chemical reaction also. That is something also that you have learned. And then which brings us to, of course, transport of species, is in terms of separation processes and reaction, right? So this transported quantities conservation is a fundamental, domain or a topic that we chemical engineers deal with on a regular basis. So the conservation equations pertaining to transported quantities is natural next step when we are looking at learning about the various conservation relationships that exist between various variables, stream, unit, and process variables. So if you are to look at transport phenomena in a continuum of fluid, and we will spend some time on this introduction to transport phenomena in a condensed fashion, since you have a separate probably a separate course usually on transport phenomena at Amrita. It is there, right? So I will not repeat what you typically learn in that course, though the same concepts will be presented from a slightly different perspective, slightly more advanced mathematical perspective, which allows for better generalization when it comes to modeling more complex systems. So that will come, and in that we will deal with what do we understand by continuum as well. But for the time being, appealing to what you have already learned about these various transport of these various quantities in fluids. So let us go ahead with this introductory lecture. In a continuum of fluid, quantities such as momentum, energy, species, and overall mass get transported due to various driving forces. There are two major mechanisms of transport, irrespective of what quantity is being transported. One is called a bulk or non-selective transport, which we generally tend to call as convection, right? So this is because the whole fluid is transported. Along with the transport of the fluid, the momentum that fluid carries gets transported, the energy that fluid carries gets transported, all the various species that are present in that fluid get transported. So this is non-selective in that sense. And then of course molecular or selective transport. There are different mechanisms or different terminologies involved in molecular transport of various quantities. When you are talking about molecular momentum transport, which again we will deal with in some amount of detail, that is due to what is called friction or shear. And then when it comes to molecular energy transport, it is due to conduction, and then also due to expansion, contraction, and due to friction. Of course, the viscous dissipation is what we call that in fluids. But even in solids, there is heating that takes place because of friction, loss of energy as a heat, low grade, high entropy form of energy, which is not available for any useful work, for example, right? So that is also momentum or molecular or selective transport of energy. Species, diffusion, and also reaction, which causes the diffusion, right? So that's what I mean when I put it there. All molecular transport has its origins in Brownian or random motion, and the contact, quote unquote, contact arising from it. And what do I mean by contact? For example, if I were to appeal to you what you probably heard in your school when you when you were told what is the difference between energy transport or heat transport by conduction versus convection. Okay, in conduction, the energy transport is due by virtue of collisions, and there is contact between these molecules. One molecule with high temperature is vibrating at a higher energy with higher momentum because of vibrations than another molecule with a lower energy, and these collisions and the contact transports that energy, some of that energy, into the other molecule, and therefore that molecule also picks up and vibrates more. And temperature is now really stretching it a little bit, but temperature is a measure of average kinetic energy, and therefore essentially you are transporting heat, so to speak. That is conduction by way of Brownian random motion, and that is also true with friction. Unless there is physical contact, there is no friction. And diffusion is also by Brownian motion, and this at some point we will take up these molecular transport processes in some detail. We will first start with friction, and then we will move on to the other molecular transports. At least we will have some amount of discussion on friction, conduction, and diffusion. Okay. So bulk transport occurs due to external driving forces. Now this could be either contact forces such as pressure difference, so there is a push essentially for a fluid to flow, or body forces such as gravity or radiation, for example. And then of course there is also geometric considerations that cause bulk transport. This is, for example, a convergence or divergence in a flow channel, or change in orientation, so to speak. Suppose you have an L bend, or you have a T junction, whatever. So there is definitely there is a bulk transport that occurs because of that orientational changes in the geometry. So the statement that I would like to make here when it comes to conservation of transported quantities any process that changes the state of a system occurs in such a manner that momentum, energy, species, and overall mass are conserved in the process. This is something, so you write these various conservation equations that capture this statement. So now if we were to look at transport through contact forces, okay, so for bulk transport through contact forces like pressure, or molecular transport for that matter, like it could be friction for instance, rate of transport of a quantity, since there is contact, we are talking about contact happening between one material and another material, so to speak. One could imagine in the continuum of fluid essentially some fluid particle and another fluid particle. In a laminar flow, one lamella, one layer of fluid and another layer of fluid, for example, right? And one cross section and another cross section, for example, adjacent cross section, for example. So there is always this transport that happens when there is contact through the surface area. So therefore, if you want to look at the rate of transport of a quantity, you take the flux, which is basically the quantity per unit area per unit time, rate per unit area, all right. And then you take the flux and then you look at how the flux is changing. The flux is a point measurement, right? It is basically, if I were to loosely use an thermodynamic parlance, it is an intrinsic quantity, not an extrinsic quantity. Rate is an extrinsic quantity. To give an example, when you say that there is a wire and that wire carries current is rate of transport of charges, and that is an extrinsic quantity. Say for example, there is a wire with a current density of say 1 ampere per centimeter square. That means per centimeter square area there is 1 ampere. So at any cross-sectional area of 1 centimeter square, there is 1 ampere current that is flowing. In other words, 1 coulomb per second, right? So that is an intrinsic quantity. Now I have not said anything about the size of the wire. So if the wire's diameter is 1 centimeter, if the wire's cross-sectional area is 1 centimeter square, then the current flowing is 1 ampere. If the wire's cross-sectional area is 10 centimeter square, then 10 into 1 ampere per centimeter square, the current flowing is 10 amperes. So now the rate of transport therefore becomes an extrinsic quantity, whereas the flux becomes an intrinsic or a point quantity. Now, which point? Now you're looking at, since this is through contact forces, the point on a surface, isn't it? So of an infinitesimal surface area ds. Now you have to integrate throughout the entire surface, and since the surface is a two-dimensional quantity, you will have a double integral. And the flux is of course, it has not only a magnitude but also a direction, all right, direction of transport. And the surface area also has a direction determined by the unit normal pointing outside. Therefore you have a dot product of these two quantities, and that dot product is integrated over the entire surface area, so to speak, and then you get the rate of transport. And this is basically S is the surface through which the quantity is transported. This is basically captured by the following figure, right? The surface S is defined at each point by its outward normal vector. So there is an outward normal vector. ds vector is normal and normal unit vector times the magnitude of that small infinitesimal surface area, which is the ds without a vector symbol. That is your surface element. And then you have some arbitrary control volume V, and S is the surface that forms the boundary of this V, and then the rate of transport of any quantity leaving, for example, that particular that particular volume. Net outflow is given by the flux of that quantity, whether it is momentum, mass, energy, species, whatever, dot product with with ds at every point and then integrated throughout, that is what gives you the rate of transport. When you have bulk transport through body forces, now this is due to gravity. For example, for momentum transport, so you integrate over the entire volume. So the entire body feels the gravitational force. So the force per unit volume is simply rho into g and integrate over the entire volume, and therefore that's a triple integral. That is the net bulk force basically that quantity is the body is experiencing. By the way, force is rate of time rates of change of momentum, that is d by dt of momentum. So that is the rate of transport of momentum. I hope you understand this. Force is rate of transport of momentum, and therefore this gravitational force is simply the rate of momentum transport by way of the bulk transport mechanism called gravity. For energy transport by radiation, now this is, of course, I have given a here. Of course, I could integrate again, double integral over the area, right? Because the radiation is received through a surface into a body, and therefore we have to look at again some sort of an integral over the surface through which the radiation is absorbed or emitted, for that matter. No species or mass transport is possible by body forces, despite what people may have seen in movies like Star Trek or sometimes even Star Wars. They use some sort of a beam, some like a laser beam, and they transport someone from one place to another. No, sorry. At least as of 21st century 2020 July, such transport by body forces of an entire object is not possible unless said object is very, very small in size and mass. Of course, that we will not discuss in this study, in this course. It is possible indeed to transport objects of mass of the order of, say, nano or micrograms or whatever it is, through application of laser beam, and with gradient in the intensity of the laser beam, it is possible to transport or trap first, and then move the trap, you transport the object. It is possible, but we will not talk about it. At least for continuum fluids, this is not possible. Okay. So flux cannot be defined for bulk momentum transport, even though it is possible for the energy transport, as I said, because the energy radiation is absorbed through a surface or emitted through a surface, so it is possible to define a flux. Whereas for momentum transport, bulk momentum transport, flux cannot be defined because it is the bulk momentum transport does not happen through a surface. In other words, if a ball is falling under the influence of gravity, the ball's momentum is not transported through its surface. All right, it is the entire ball that is falling. It is for the entire body of that ball. So it is like a rigid body motion, like that. Gravitational force is also, it's experienced uniformly by the entire body of fluid, and therefore it is not possible to define flux for a bulk momentum transport. Now, transport through geometric effects, this also we will see in some detail, but here I'll just give a very brief introduction. Consider a fluid is flowing through a channel, and this bulk flow is termed convection, right? This is the present inertial state of the fluid. You look at Newton's first law of motion. Unless some external force is applied, basically this state of motion, uniform motion, will continue to be the inertial state. Now, let us first define the convective fluxes. For mass, it is rho into V, or rho I into V. That is basically kg per unit area, say meter square, per unit time, which is say second. So this is kg per meter square per second, and that is simply given by kg per meter cube, which is your density, multiplied by meter per second, which is your velocity. So rho v is mass flux. You have studied this in your mass transfer courses. And for any given species I, if the bulk velocity, convective velocity is v, rho I into v, which is the density of that particular species in that volume. So if there are 5 species in that volume, how much mass of that one specific species alone is present in the whole volume, right? That mass per unit volume, that is rho I multiplied by v. Momentum, okay, rho v into v, and again you can understand this by looking at it one of two ways. One way is to say that rho v is basically mass flux, and mass into velocity is momentum. Therefore mass flux into velocity is momentum flux. All right, so that is one way, perfectly okay way to look at it. Right, then the next is energy flux. So you now start seeing a trend. The mass per unit volume is rho, multiply that by velocity, you get mass flux. Momentum per unit volume is rho v. That is the second way to look at momentum flux. Mv is momentum, mv divided by capital V, which is the volume, that is the momentum flux per unit volume, that will be rho v. You multiply by that by velocity, you get momentum flux. So similarly, you should have, suppose your U here is internal energy or some form of energy per unit mass. So m into U, for example, m into Cv into T, or if this is enthalpy, m into Cp into T, right? So that should give you basically CPT or CVT being heat capacity, right, per amount of energy contained per unit mass. All right, now that would be U, multiply by the mass, so we'll give you joules, right? Joule per kg into kg should give you joule. Now you're looking at energy per unit volume. Energy per unit volume, therefore you divide the whole thing by volume, so you will get rho into U should be the energy contained in the fluid per unit volume. Multiply that by the velocity, you get energy flux. So here rho is density, I is the subscript for individual species, v is the velocity, and U is the internal energy. Now we are looking at bulk transport of fluid, and along with it the transport of overall mass and species and energy and momentum, right? So consider a fluid that is flowing through a channel. This bulk flow is called convection. When the fluid is flowing in bulk motion, that is the present inertial state of the fluid, unless some external force acts on it to change that inertial state, as given by Newton's law of motion. Keeping in mind, I'm going to present two cases. One case, basically a macroscopic phenomenon where there is a channel geometry change. There is a sudden expansion or contraction of the geometry of the channel. For example, this could be when a river which flows either widens or narrows. And this is well known in rivers. When you cross a river, the path that the river, the crossing distance varies. The cross section, so to speak, varies at different points along the river. So the channel continuously keeps changing its width, right? So suppose this happens, this would cause the bulk flow of the fluid to either diverge if the channel geometry widens, or converge if the channel geometry narrows. So this much is clear, right? So this means that the convective momentum that is being carried in a certain direction, let the flow direction be say x, and now because there is a widening or a narrowing of the channel itself, there is a change in the y coordinates of the boundaries. So if the channel were defined by, say for example, the center of the channel is defined as y equal to 0, and one side is say y equal to plus delta, the other side is y equal to minus delta. Now this magnitude of delta changes, right? So as the channel diverges or converges, right? So therefore that means there is now a transport of x momentum in the y direction, isn't it? Either in the plus y direction or minus y direction. Until this widening or narrowing happened, the fluid was all flowing in x direction, so the entire transport was in x direction. All right, now suddenly there is a diverging, and therefore some amount of momentum is now taking a turn towards the y also. So now you can resolve the momentum. Now if you look at the velocity profile, for example, you can resolve it as having a Vx component and a Vy component also. And this sort of a change means momentum is now transported in the y direction. And similarly, if you are looking at other quantities also, any species that is present that are present in the bulk fluid are also transported now in the y direction. Energy is also transported in the y direction. The overall fluid, of course, the overall mass is also transported in the y direction. And this sort of a change would be given by divergence or convergence of the flux of that quantity, isn't it? So this would be captured by these quantities, the divergence of mass flux or species flux or momentum flux or energy flux. Now this is one way of looking at it, one specific case where this sort of a term becomes important in considering the conservation equation. Now let us not worry about the large channel geometry. Let's not look at this whole thing from a macroscopic perspective, but shrink this to some infinitesimal volume of this fluid, right? Where of course still the continuum hypothesis holds. As I mentioned in one of the previous slides, we will of course have a separate discussion on continuum hypothesis itself, appealing to your prior understanding of continuum hypothesis, that the fluid may be treated as a continuous entity, its properties may be treated as a continuously varying in spatial positions and with respect to time, and that there is no discreteness, so to speak, that we have to consider, right? I will leave it at that for now. So assuming that continuum approximation or continuum hypothesis of the fluid, that model of a fluid holds in that infinitesimal volume, all right, within that infinitesimal volume, what does this divergence capture? This divergence captures essentially the exit of the fluid outside the infinitesimal volume, or coming in the entry of the fluid into the infinitesimal volume by through the surface that bounds or that covers that volume. So there is a boundary for this volume, right? If you were to look at it as a control volume, typically you would have drawn a shell balance and you would have drawn two lines, parallel lines, something coming in, something going out, right? So that essentially that actually captures a cross section, isn't it? And the thickness is infinitesimal, and therefore you don't worry about that part of the surface. So there is these cross sections that are there. So through those surfaces, the fluid comes in, the fluid goes out. So the net fluid that exits or enters this small volume, infinitesimal volume, is captured by this divergence, right? By actually this flux. Actually, if you want to capture that the net amount of fluid that comes in, you should take the flux, which is, for example, the mass flux is rho v, integrate over the entire surface area. That would be a double integral, and that will give you the flux. All right, we will see why this divergence effectively captures that particular the net inflow or outflow of either overall mass or species or momentum or energy later on, when we look at this derivation of the conservation equations in some detail. But this phenomenon is effectively also captured by these divergences. all right, or at least they are represented in the conservation equations through these divergences. Now let us move on to the conservation equations themselves. Now if you were to look at conservation of overall mass, now you are expressing this total mass of the system as mass per unit volume. So given expressed as density, this way basically you are now looking at it as, you know, in the thermodynamic parlance, an intrinsic quantity rather than an extrinsic quantity. So it doesn't have anything to do with system size. So this equation should be valid as when you derive this equation, when you obtain this equation should be valid even for a point volume or for any large system as well, right? So it is independent, the validity of this equation is independent of the system size, so long as continuum hypothesis holds, because this is obtained within the framework of continuum hypothesis, right? So therefore this all these conservation equations are expressed in terms of such intrinsic quantities as I had discussed before, right? So now we are looking at total mass as density, mass per unit volume. Now the typical formulation is what is the net rate of accumulation or depletion of the total mass in that volume. It is given by total mass coming into the volume minus total mass leaving out of the volume by convection, by bulk flow, and there are no specific selective molecular flow mechanisms for the total mass, right? They could be there for individual species, they could be there for momentum, they could be there for energy, but for the entire substance it's only the bulk flow, and there is no source or sink, in other words. Therefore mathematically this is expressed as dou rho by dou t is equal to minus del dot rho v. Now so this left side term is the rate of increase of total mass per unit volume, that is the left side of the equation given in green font, and the right side of this equation is the net rate of total mass addition per unit volume by convection at a velocity v, that is the total mass in minus total mass out. So this is what I was trying to explain in a couple of slides back, in that the net rate at which a fluid is coming in or out by in a control volume, a small infinitesimal volume, that is captured effectively in the conservation equation by this divergence term. And how this mathematically happens, is something that we will see in a future lecture. Just to point out that the actual flux is basically rho into v, and the rate of net rate of mass addition is actually double integral of that rho v over the ds surface, right? However, this is how it is captured in the conservation equation. We will see why that is when we look at the actual derivations. Now if you were to look at conservation of species, now we are looking at conservation of a specific component mass of species I expressed as the density of that species I. So if you have a total volume of say 1 meter cube, there are 5 components. Now you are looking at what is the mass of that particular species I in that 1 meter cube volume, right? So that is your species density. Now if this were instead of mass, if I were to look at moles, this would have been moles per unit volume of that particular species. This would have been called concentration of that particular species. That would have been the molar concentration. This is the mass concentration, so to speak. Now if this particular conservation equation is written, again you will have rate of net accumulation or depletion of that particular species per unit volume is given by mass of I in that volume coming into that volume minus mass of I leaving that volume by convection again. And now you are looking at, since it is species, now you have selective transport mechanisms. First transport mechanism is diffusion. So net rate of addition of mass of I into that volume by diffusion. The second is by generation or consumption by way of some homogeneous reaction in that volume. Or if you have, maybe you may even have catalytic particles that are dispersed so finely that you are going to treat that whole system as if it is a homogeneous system, and the reaction may actually occur at the surfaces of the catalytic particles. Nonetheless, doesn't matter, some sort of equivalent homogeneous reaction, right, by which the species I is either generated or consumed. So what is that rate? That is the next term that gets added. Now mathematically this is expressed as, so on the left hand side again you have basically the rate of accumulation or depletion of mass of that particular species I, given by dou by dou t time rate of change of rho I. And then one is the convective term, which is del dot rho IV. The second is the diffusion term, which is del dot JI. Notice similarly the flux, diffusive flux is JI, which is typically given by Fick's law of diffusion, and yet there is a del dot term here. We will see the how that term essentially captures the net rate of addition, right, in the mathematical equation, species conservation equation, in a subsequent lecture. The third term is, of course, Ri, which is the rate of generation or consumption of that particular species. Now, if I were to look at energy, again, now I have to look at energy per unit volume. And now U here is internal energy per unit mass. Okay, so that is how it is defined. This is basically the it is basically the molar internal energy, something similar to that, but of course it is defined per unit mass instead of per unit moles, and then you multiply that whole that quantity by the density. Now, if this were molar internal energy per internal energy per unit number of moles, then you would multiply this term by the net concentration of all the species that are present. So basically this is the internal energy per unit volume, and this is again an intrinsic quantity. Now if you look at the rate of internal energy accumulation or depletion per unit volume, this would be given by the net rate of addition of internal energy into the volume by convection. Now in this I am writing both the in term and the out term. So the in minus out is captured in this one term. So this is the net rate of addition of internal energy into that particular volume by convection. And then you have, of course, there are some selective specific molecular transport mechanisms of energy. First one that we are looking at is conduction, right? And then you have the reversible rate of addition of internal energy in the volume due to compressive work. What does this mean? This is really when you have a compressible fluid. Now that compressible fluid may undergo a local compression or expansion, like for example compression rarefaction, when you are trying to propagate sound waves into air or any kind of compressible fluid for that matter, right? So this sort of, there will be local compressions and local expansions, which basically will result in some sort of a reversible rate of addition of internal energy into the volume, that is typically given by integral PDV kind of work, right? And then there is of course friction, which will cause loss of energy, right? The energy that is contained in the system is now converted into a dissipative lower quality energy, which is not available for any form of work, so to speak, and that is the dissipated energy. For example, you have viscous dissipation by shear stress. The simplest example I can give is how you warm your hands by just rubbing your two palms together, right? So the heat that is generated, that is basically due to the irreversible frictional forces that are there between the two palms that are in contact with each other, and that is your irreversible rate of addition of internal energy in that volume due to viscous dissipation. Now mathematically this is given by this particular equation, where now the left hand side is basically the rate of internal energy accumulation and depletion. Then the convective term, you see, has a very similar structure to the convective term for species as well as for overall mass, right? So the del dot rho uv, right? And then you have a conduction term, which is basically your selective molecular energy transport mechanism. Note that this has the similar structure to what you saw in species for diffusion, del dot ji, right? And then you have two additional terms when it comes to energy. One is the pressure based compression expansion kind of work that is given by P times del dot V. And then the last one, for the time being, you may see some colon there, and the mathematics may be unfamiliar to many of you. Now, we will in one of the subsequent lectures, we will get a very preliminary introduction to these quantities tau, which is shear stress, and del v, which is velocity gradient, both of which are not typical vectors, but they are actually second order tensors. And we will get an introduction to why they should be tensors and how are tensors represented, and what is this double dot. It's basically called double dot product. So this basically gives a scalar quantity. You notice that all the other terms are scalars, so this also will be a scalar. So what this means is something that we will learn in subsequent lectures. But this term effectively captures the irreversible rate of addition of internal energy in the volume. Now, the next thing is conservation of momentum. Now, again, now we have to look at momentum per unit volume. That is simply rho into V. Mass per unit, mass into velocity is momentum, and momentum per unit volume is simply rho into V. Now you look at again rate of momentum accumulation or depletion in unit volume is equal to momentum into the volume minus momentum out of the volume by convection. Now this term captures the net addition of momentum into a volume by convection. And then you have, I have put two sort of contact based transport of momentum. One is pressure gradient that results in bulk flow, bulk momentum transport, and the other is a shear which results in selective molecular momentum transport. And then there is also, of course, the external body force that exists per unit volume, which is basically the gravitational force. Mathematically, this is given by dou rho v of dou by dou t of that momentum per unit volume is given by these terms, and they mean what their meanings are indicated by the arrows. Once again, I would appeal to you to observe that this del dot rho v has a similar structure to all the convective terms that you've seen in energy, del dot rho uv, and then del dot rho v itself, and del dot rho iv in terms of species. So there is that similar mathematical structure. And then when you see this the shear term del dot tau, and that has a similar mathematical structure to the selective molecular transport mechanism of this particular quantity momentum, that is del dot tau, which is similar to del dot q in energy, which is basically q being the energy flux, probably given by Fourier's law of conduction, and here tau may be given by Newton's law of viscosity. And in species transport, you had del dot ji, which j is given by Fick's law of diffusion. So they all have a similar structure. And then you have, of course, the rho g, which is the external body force, and del p, which is the pressure gradient. So with this, we come to the end of this rather long, densely packed and sort of big picture introduction to conservation equations. I hope you understand the reason behind putting all of this into a single lecture rather than breaking this apart. So that you can. The idea is to sort of highlight the existing connections, interconnections, and similarities between the various conservation equations of the different conserved quantities: mass, species, energy, and momentum, right? And once that understanding is clear, then maybe when we go and take a little bit of a deeper look in the future lectures about how these equations come about, and then how they are applied in some very practical problems, then you can start seeing how the same physics starts manifesting in different problems in different ways. I hope this lecture, even though it is long, you may have to listen to it maybe a couple of times, few more times, because it is packed with information. I hope you are able to follow it. Now, in case you have any questions, please, as usual, feel free to contact me. You can leave them and comments. Please welcome, leave them on the comment section below on the YouTube channel, or if you can reach me individually, then that would also be welcome. Thank you very much for listening to this lecture. I hope you have a wonderful day. Thank you.